So what I'm going to talk about today, a bit about industry context, why heat networks, then I'm going to show you what heat networks can achieve in terms of their operating conditions, and then I'm going to get into the detail of energy strategy in the current context, what do we need to be thinking about in terms of heat pumps and approaching systems, and then a little bit of a summary of CIBSE released CP1, the Code of Practice update last year, and just going to pick out some of the key things to be aware of in terms of designing heat networks, and then just a closing note on delivery, but the majority of the focus is on energy strategy and design. So just to get everyone on the same page, what we're talking about from a low temperature heat network perspective, and the kind of phrases I'll be using. If we look at the first on the right hand side, that's typically known as the tertiary system, which is where we've got our space heating and our hot water systems. That's separated by our heat interface unit, which separates the hydraulically separates the heat network from the dwelling itself. Sometimes we have substations, so further hydraulic separations, typically only needed for tall buildings when the static pressure gets so on to break up the pressures. Sometimes they also use for contractual demarcations between someone that owns the primary system and someone that owns the building level system. And then we have energy centre with our generation. Sometimes we have multiple energy centres, but most of the time it's located at just one central plant that serves heat to the entire development. And normally the demarcation of primary and secondary is the energy centre to a substation, and the secondary is really talking about what's going on in the building. So why low temperature? Why is it? It's a massive growth area for the UK and has been for a while, and I think will continue to be for a long time. Obviously, decarbonising heat is a big challenge, and heat networks can play a role in that, and they have been shown to play a successful role in that in areas such as Scandinavia, where if you look at how they've decarbonised heat, they put in heat network infrastructure a long time ago. And actually that was initially put in on fossil fuel infrastructure, but now they've managed to introduce low to zero carbon technologies into that infrastructure, and the carbon profile of their heat is significantly reduced as a result of that. And the reason that is the heat network are technology agnostic and permissive. So we can use the heat network infrastructure in terms of the pipework that's serving the dwellings, receiving hot water. That can receive hot water from any type of technology. It can be a gas CHP, as has been for a long time, or it can be, low to zero carbon technology such as air source, ground source pumps, or energy from waste. So we can put the infrastructure in. It doesn't necessarily have to be optimized on day one in terms of its low to zero carbon generation, but over time we can transition that generation technology. So it's a really agnostic infrastructure that we can use to decarbonize over time, not just get an instantaneous gain in terms of the design. They allow managed interaction between power and heat. I've seen a lot of that with the CHP, and I think we'll continue to see that in terms of some solar PV, maybe combining with heat pumps. But I think the most important thing for the UK in terms of the trajectory and how do we make the most of this is we know how heat networks work now. There's been some problems with heat networks, but actually as a country, we're starting to be quite a long way down the experience curve of how to get heat networks operating well. And so to then take that knowledge, build upon that, to use that as a really strong, attractive platform to decarbonising is something that can be quite powerful for the country. If we talk about decarbonisation of heat in the UK and we look at across section of housing density that we're going to have some very low density housing, new build and existing, and that's predominantly going to see individual heat pumps come in as its primary solution for decarbonising heat. They can be a variety of air source, ground source and water source, but I think the major rollout is probably going to be individual air source for low density housing. And then we've got our medium and high density, and this could be high of flats within city centres or towns, but then also more rural locations, developments of terraced, semi and detached housing, say 30 dwellings per hectare. They're still attractive for a heat network to supply cost-effective low carbon heat, and that's predominantly what I'm talking about today, is those medium to high density systems where a heat network stacks up financially, that's what I'm going to be talking about today. And moving forward, the role of heat pumps is going to become dominant in terms of gas. CHP has largely had its day, to be honest, in terms of the low carbon technology, and it's very much the day of the heat pump now and will be for a long time. So how do we get ready for that? I wanted to put this before going into talking about how to strategize and design heat networks, because I think it's important to appreciate, well, what can they look like. People are on the call, but there's probably quite a mix of experience and maybe hearing other people's experience of heat networks, because there have actually been quite a few poor performing heat networks, but that doesn't mean that that's necessarily a characteristic of the technology. It's more linked to the mistakes made about delivering those schemes. But when you do them right, they can work really, really well. This is a scheme that's been through our full design specification and quality assurance process. It's a joint venture between Origin Housing Association and Hill Residential. So it's the North Holt Road project. So it's a residential system in London. And this is the flow and return temperatures from this heat network on day one of operation. So basically just before handover, after the commissioning was complete. And what we've got here is the blue line is the flow temperature of the network. So this is what the heat energy center is sending out. This is actually gas CHP gas boiler system. So we're sending out 60 degrees to the system quite stably. And that 60 degrees is a low temperature for heat networks. Like 5 years ago, they were coming through at 80 degrees, and then we had a period of 70 degrees. And now what we can get them to is 55 to 60 degrees. And this is very achievable. But also the return temperature, which is the green line. Variable is okay. That will variable depending on whether people are using hot water, where you get very low return temperatures, or if they're using space heating, it might be slightly higher, but creeping above 35 degrees, and it's an average of about 30 degrees. So this is a 60-30 heat network that was planned at design, was specified that key characteristics of how to get those low temperatures of 60-30 planned all the way through, and then tested prior to handing over to make sure that it was delivering 60-30. And a year later, that operation is maintained consistent. So 12 months after handover and occupation, still seeing that 60-30 temperature profile. And this is what we're going to need to see in the UK in terms of the heat networks that come through now. So low temperature means low losses, means more efficient, so lower carbon impact, but also lower cost of and lower risk of overheating and all the complaints that are associated with that. So just put into context in your mind, you might have heard about horror heat network, 80 degrees, 78 degrees return temperatures, overheating. There's things that can be done to avoid that from happening, and that's largely what I'm talking about today. So when they're done right, they're an excellent vehicle for giving residents high performing and cost effective low carbon heat. So energy strategy first, how to plan and de-risk. Just before we get into this, about 18 months ago, we found that our clients we were getting changes to SAP, so how carbon was being treated, had the new consultation around changes to Part L and the changing in building regulations, and we knew heat pumps and CHP was going to be displaced in terms of the de facto low carbon generation. That was, and it still largely is, that was a massive amount of uncertainty to deal with at once for developers. And we started getting heavily involved with advising developer clients and housing associations on how to strategize and de-risk this change and still deliver cost-effective, low-risk systems for its residents. So this is largely where that has come, working our way through that high-risk, high-uncertainty environment, finding a way through that makes sense. So some of the key messages are, it can be really easy to get attracted to the energy centre and want to go straight into the heat pumps and start thinking about how to design the heat pumps, when actually it's the dwelling that's defining what does our heat network need to do. So when you're designing and strategizing a heat network, you need to start with the dwelling and work back from that dwelling to determine what the energy centre needs to do. So work from the dwelling backwards. You can also largely standardize and de-risk that dwelling and that end user, and actually the envelope of the building in terms of that secondary system, you can arrive at a set of design approaches and decisions you can repeat across lots of developments, and you can de-risk a large portion of that development, and then focus on the novel stuff, so the energy centre. So you can get the buildings well de-risked and standardised, and then focus on the novel stuff. Assess and review optimal generation strategy. This is about, and I'm going to talk about this in detail. You know, are we going 100% heat pumps? So we're doing a hybrid system where we've got heat pumps and boilers, and what's the role? Getting into actually the nuts and bolts of how do you select a cost-effective system, one that is largely decarbonising, but is also thinking of the end cost to residents, and that needs a lot of care and thought. And the last one is, I've seen a lot of options just early for, you know, it could be ground sources too expensive, when actually you get 12 months into the design program and it's realised that the rooftop value of that building was actually far more significant than it would have cost to put the ground source in, because maybe there was you know, commercial space up there, leisure facilities, amenity space. So make sure you're optioneering at the start and giving that due attention, not taking stuff off the table quickly that you might come down the road later on and realise, oh, that might have actually been quite a clever solution. So really do the due diligence up front. About the dwelling and the buildings. What a low temperature heat network example for how you can give quite a blueprint for your buildings, particularly in the residential sector. You know, we can get domestic hot water delivery temperatures down to 50 degrees now, and I'll talk about that a bit later. But that permits us to run our network at low temperatures. You know, you can select your standard space heating emitters, so preferably underfloor heating, and I'll talk about that later, but also can be low temperature radiators. But you can make those decisions and standardize them moving forward. And we can make a lot of decisions that basically allow us to say, okay, we know we can get a 55 to 60 degree heat network to serve this, and we can use a standard system, proven system with operational data at a dwelling and a building level. And now we can focus on what's our fuel mix, what's our generation mix, what's the role of boilers, where are we going to locate this plant room. But my dwellings and my buildings are actually fairly standardized and deep for a low temperature heat network model. When we're looking at heat pumps on a heat network, we need to start thinking around what's the difference between a peak generation plant and a baseload generation plant. The challenge with heat networks, particularly with heat pumps, is they need to be designed to cover the worst case peak load event occur essentially when it's, say, -5 degrees outside on the cold day of winter, and 6-7 heat programmers kick in, but also the shower load kicks in and we get a hot water event and a heating load event. The challenge is the system needs to be able to cope with that incredibly infrequently for a very short duration. So with a plant that's designed to cope with this event that happens on a very rare occasion, and the vast majority of the rest of the time throughout the year, the load spends its time much below that. And this is what this graph is showing, is that we've got our site demand for a typical 500 dwelling scheme, and the peak demand for this, let's say 1.2 megawatts. If you look at the cumulative number of hours per year spent at or above a given site demand, you can see that for half the year, we're at loads less than half of that peak load. So we're spending the majority of our time at loads well below the peak load. So when we look at this in more detail, we're spending 90% of the heat demand below 45% of that peak. We spend 8% of the heat demand around 35% of peak. And we actually spend 50% of our heat demand is occurring below 20% of the peak demand. When we start sizing heat pumps for systems, heat pumps are fundamentally expensive technology. Compared to gas boilers and compared to gas CHPs, they're significantly more expensive. So, you know, a gas boiler with fluid all in, you're probably looking around £100 a kilowatt, whereas an air source heat pump system, you're probably looking at more £500 to £700 a kilowatt. So when you replace for something like this, let's say 1.2 megawatts of gas boiler with 1.2 megawatts of heat pump, that cost profile suddenly shoots through the roof. And that can be quite difficult to accommodate. But actually, when you think about it, you're buying all of that heat pump plant to sit there basically doing nothing for 90% of the year. Well, you're certainly buying half of it to sit there doing nothing for 90% of the year. Things we can do a bit more intelligently than applying those kind of approaches to design. What we can do is we can size a heat pump at more like 20 to 25% of the peak demand, and that heat pump will actually deliver us, when we combine it with a decent sized thermal store, 80% of our annual heat demand. So we're rationalizing the size of that heat pump down. We're providing it with a thermal couple when that heat pump can run from when the demand occurs, so we can extend the running hours of that heat pump, and we're getting a lot of kilowatt hours per kilowatts from that heat pump. So that's a big reduction in how much we're spending, and also the space to accommodate, but we're actually getting that heat. And then we can size a boiler, which looks quite big. It's 1 megawatt of boiler in this example, compared to 225 kilowatts of heat pump. But that boiler is there for a specific purpose, to kick in when that heat goes above a certain demand and it needs to support it. But it's only doing 20% of the demand. And when you think about the carbon impact of that, the heat pump's doing the heavy lifting of the decarbonisation, and the boiler's kicking in there to support it, but it's not really doing the majority of that heat demand. I can push that even further, particularly, if we want to really push the boundaries of asking the heat pump to do 95% of my annual heat. But I only need to increase my heat pump capacity from 225 kilowatts to 350 kilowatts in this example. So it's 35% of peak demand, but it's doing 95% of my annual heat. So I can get it to do an extra 5%, to do 100% of my annual heat. But in order to do that, I'm pretty much going to have to go from 350 kilowatts of heat pump up to a megawatt to 1.2 megawatts of heat pump. So you see how much marginal gains you're getting in terms of decarbonisation and heat contribution as we try and creep up what we're asking the heat pump to do in terms of this peak load curve. And so finding the right point on your schemes in terms of the ones you might be consultants supporting developers on, or if we've got developers on the call, thinking about what you want your strategy to be in terms of the heat fraction from a heat pump compared to maybe can be a gas boiler, can be an electric boiler, is a really key decision in terms of the cost profile from the scheme, but also the cost profile for the residents that live on the scheme. Setting up a scheme like this to do a hybrid system where heat pumps are feeding in 95% of the heat doesn't stop you in the future bringing in something that replaces that gas or electric boiler top-up load. And this is the beauty of the heat networks, going back to the fact that they're so technology agnostic. But you can go 95% of the way there on day one and not get too caught up in this 100% heat pump concept and not really get significant benefits over a hybrid strategy. So it's one to think through quite carefully when you're strategizing heat networks. The other one is technology. I'm not going to talk about this in loads of detail, but on most projects, this will come up in terms of, okay, we're doing a heat pump into a heat network. Are we doing air source, or are we doing ground source, or are we doing, water source heat pump or energy from waste feeding into a heat pump? Predominantly what we're seeing is air source heat pumps, and that's largely driven by the fact that air source heat pumps are the lowest cost pound per kilowatt compared to ground source and water source. However, what I would say, going back to that point of do the due diligence of what your scheme specific needs, sometimes those other technologies and those other cost profiles actually stack up. So air source heat pump, low capex, not really going to have any impact on ground level space, but a big impact on roof level space. So big piece of equipment that on a previous block of flats didn't need to be accommodated now have find space for it, and sometimes that rooftop space is incredibly valuable for other purposes. And so finding an alternative to avoid having to locate that on could mean that you look at ground source or water source if you've got like a reservoir or a water source in the area. Also, ground source can sometimes offer you more efficiency. The overall seasonal coefficient of performance compared to air source of ground source has typically been higher, although I think with innovations in air source, CO2 heat pumps and dropping down temperatures, that gap may start to diminish. But again, that's something to look at in the comparison. This slide is actually out of date because and ground source that did make ground source quite attractive is no longer available. So it is, in my mind, becoming slightly harder to ground source, and we're seeing developers go to air source because of that. But as I said, there are sometimes several drivers where ground source will actually be the better solution. From my personal perspective, I'd like to see a lot more water source come through, particularly in London when there is a lot of nearby water sources, such as obviously the river, but also docks, canals. I think the fear of getting permits and going through that process of getting to actually install a heat pump, heat exchanger within the, going through the policy process is a little bit of, so I think there's quite a lot of work that needs to be done in terms of lobbying support from kind of canals and river trusts and that sort of thing to get a bit more of an open door to getting access to some water source, because we're going to need to put it in the mix. So that's energy strategy. As I said, big change for the industry, a lot of uncertainty, quite high risk in terms of you can suddenly find your cost profile, your per dwelling or per building cost profile of a heat work go through the roof. But thinking through the right strategies, thinking about hybrid systems, that can be a clever way of working through that uncertainty and finding a way to transition to heat pump technology rather than kind of jumping off a cliff and suddenly finding yourself doing 100% air source heat pumps on a scheme where you've not done it before. So think that carefully through and advise your clients accordingly. So on to design. What I'm talking about now is largely predominantly around the dwelling and the building design, because that's, as I said earlier, what defines what the heat network needs to do. But not just that, we actually find that it's the dwelling and the building in terms of their design and performance and commissioning that will dictate how well the heat network performs. When a dwelling is not performing well, the whole network suffers and there's nothing you can do about it in the energy centre. And so there's a lot of attention that needs to be given to how do we design dwellings and buildings, and how do we size those dwellings and buildings correctly to get the overall system to work. And by the way, I can see all the questions popping up, but I think the strategy is to cover those at the end. So hopefully we can get to those one by one at the end. FairHeat have been supplying developer and housing association clients with our FairHeat heat network design supplements for a number of years now. And this document goes hand in hand with the code of practice. It's with over 30 housing developers and housing associations. And it basically, the code of practice is a very wide-reaching document. It covers everything from a communal heating system with 10 to 20 foot district heating system, and there's lots of different options in that document, whereas our design supplement is a way of sitting down with the developer and going, what do your developments need, what is the nature of those developments, so how to make specific decisions for you to then roll out for your systems, but still be compliant with CP1 2020. So closely aligned with CP1 2020, and it's strongly linked to performance objectives. Next. If we want a heat network to work well at the end, we need to define what that performance is at the start, and we need a method of saying this is what we want the performance to be once we get to the end, and a quality assurance process is in place that makes sure as the system hands over from different stakeholders, so strategy consultant, design consultant, installation contractor, commissioning engineer, that those performance metrics are tied all the way through. And the key is to make those performance metrics contract by placing it with consultants in employees' requirements and contractors in their employees' requirements. So this is what the design supplement does, is it sets out performance requirements, benchmark and framework of how do we get that end-to-end performance from conception to delivery. The design supplement itself is structured around 5 core design principles. Minimizing losses. This is one of the issues that's plagued heat networks in the UK is excessive losses from the distribution system. This is linked to excessive operating temperatures at design, but also elevated return temperatures, which basically means half the network is losing more heat than insulation applications that are inadequate, but then also insulation that's not installed correctly. So we have gaps in insulation, we have insulation that's too thin, and that's led to a lot of schemes with quite a lot in terms of high heat losses, which obviously raises the carbon footprint of the system, but also raises the bills to residents. Things like overheating and resident complaints. So minimising losses is absolutely core to a successful heat network. It's been quite challenging. The industry is oversizing. So when we oversize a heat network, that peak load profile that I showed you, where we spend very little time at the actual peak load, if I make that oversized by even 300%, I'm exaggerating that profile even more and putting even more kit that's sitting there doing nothing. And we want our plant to be operating at its design condition, or as close to as much as possible. If I kind of stretch that and put in a megawatt boiler when I actually only need 100 kilowatts, it's not going to operate. Also, if we don't size appropriately, our pump too big, and then we get a high surface area and we lose a lot of heat off those. So it goes back to minimizing losses. So getting the system sized correctly is absolutely critical. Reducing complexity, this is around making decisions that sometimes remove kit entirely to reduce complexity, but make the system operate more efficiently. I mentioned sometimes we have network substations. They need strong justification, because every time we put in a hydraulic brake, we have to have a temperature difference of hydraulic brake to transfer heat across that plate heat exchanger, and that raises my generation temperature. So that raises losses from a heat loss perspective, but from a heat pump perspective, it makes it even, because we want our heat pumps to be operating at a lower temperature as possible. So making decisions that reduce complexity and that are justified is also a key part of the document. Design for resident comfort, I think, is a really important one. It's residents that are living on these heat networks, and if we can't get them operating to a satisfactory state, they're not going to be supported by the government, and they're not going to be there as a vehicle for decarbonisation. It's absolutely critical that they are for us to hit our targets. So making sure that the resident comfort is to a suitable level is part of the document as well. And then I come back to this measurement of performance. We're going to define the performance in terms of key performance indicators on losses, flow temperature, meter read, stability. But if we define a metric that we want to be linked to performance, we have to be able to measure it. And that goes back to the metering strategy we put in place, the data we can extract from the system, where those heat meters are located, how frequent the data can be pulled. And so there's also a lot in the document around how do we specify a monitoring system that we can actually monitor the performance and measure it. So going into these in more detail, minimizing losses, this is around 4 key things. So we want to minimize the network length, which is obviously driving reduced surface area of the total network. So we can reduce the network length, we can get losses down. Reduce our operating temperatures, so double whammy now, but lower operating temperatures mean lower losses, but they also mean a more efficient heat pump. Minimizing pipe sizes, again, surface area, bringing that right. Just talking through some of these in turn, in terms of linking back to what CP1 2020 is pitching on this revision. One of the ways we can reduce network lengths that hasn't been taken up much in the past, but is really starting to gain traction, is particularly within blocks of flats, the way we configure. The one on the right is a building with, okay, we've got 4 flats per floor. We've got a single riser coming up one side of the building, and then we've got our corridor level pipework that's going to be in our ceiling voids, dropping into each of our apartments. If we move to the one on the left, we'll significantly reduce the total length of our network. This corridor pipework and the terminal run pipework, and by the terminal run I mean the bit that leaves the corridor and goes into the HIU, makes up the significant majority of the total network length. And I've got a chart to show you on that, just to put that into context. But looking at this in plan view, we can the is the worst case, let's say. So we've got one riser and we've got HIUs located at the opposite ends of our apartments from where we're coming in with our terminal runs. So we've got a lot of pipe work per floor to get from our riser location to where we need to serve heat into the apartments. We can drastically reduce that by bringing the HIUs local to the corridor, and you can see the impact that's had on the amount of red pipe work. But the big thing is, just by doubling up the riser, from moving the riser location from the central location and splitting it to 2 locations in the amount of red pipe work per floor has dropped significantly. And all I've really added is, for a floor height of 3 meters, an extra 6 meters of pipe work compared to the single riser, because I've got a set of flow and returns. And this pipe work here would be closer to a total of like 20 to 30 meters per floor. So I'm saving a significant amount of pipe work. That reduces capex, but it also reduces losses. When this really hits home is when I think about my riser, which is my vertical length of pipework going up and down the building, my lateral, which is my corridor pipework in the ceiling void in the corridor, and my terminal run, which is that last bit going into the HIU. My corridor and my terminal runs, typically on a block of flats, make up 75% of my total network length. So if I can largely cut out that network portion, I'm going to be reducing my network length by 75%. So there's a huge value on the table there by strategically thinking how I want to lay out my heat network. Another that's gaining a lot of traction in the industry is, rather than locating the HIU internally, we actually move it to be located within an externally accessible cupboard within the corridor. Now, this drastically reduces my terminal run length because I'm no longer going from the corridor into my utility cupboard, but it also gives heat network operators much more readily available to the HIU. And one of the biggest costs to network operators today in the UK has been getting access to problem HIUs. So there's a lot of benefits to moving those HIUs to be located externally. The challenge is, this is architecturally something very different to conventional design, and it needs to be planned at REBA 1 and REBA 2, and you need to get the architects involved and supportive of this approach. To REBA stage 3 and 4, it's nigh impossible to leverage into the scheme. So something that can have massive cost and operating cost benefits, but needs really, really early consideration in the design program and needs support from the developer, but also the architect. But you should see a lot more of that coming through, championed by the approaches set out in CP1 2020. Spoken about pipe sizing, obviously for a given load that we need to supply to a dwelling or a corridor or a building, if we can make that pipe size just one size smaller, but still be able to comfortably supply that load, we're going to be reducing our losses by 10 to 20% for that given section of pipe. So getting pipe sizes accurately sized, but also sized sensibly to deliver will have a big impact on heat losses. There's been a big movement in CP1 2020 in terms of how pipes are sized. Again, it goes back to that short intermittent nature of peak load, that the pipes have to be sized to be able to deliver, but most of the time, obviously we know they're going to be spending at loads a lot lower than that. So we've actually moved to a velocity-based pipe sizing approach rather than a pressure drop sizing approach. So typically in the past we would have like 150 or 250 pascals a meter as a pipe sizing benchmark, whereas a velocity approach, sometimes you'll actually be up at more like 1,000 pascals a meter. But when you just apply that to the network extremities, like terminal runs and lateral runs, in terms of the impact of your index run on your pump, that length of the final corridor and terminal run is not very long. So from a pressure drop perspective, you can actually accommodate quite high pressure drop per meter parameters without resulting in a big impact on your selection of pump. As you come back from the dwelling and corridors and also down the riser, obviously your length of pipework is starting to get longer and longer. That's impacting on your index run and the selection of your pump in terms of the head and differential pressure it needs to put into the system. And so eventually you will move back to more of a pressure drop based approach. But what you really need to do is a life cycle assessment of how do I optimize my sizing of pipe work in terms of reducing losses, but versus not resulting in a way oversized, also has extremely high parasitic loads that's offsetting those heat losses. So really big steps for CP1, and we should start seeing a lot more appropriately sized network distribution systems that will drive down losses significantly. But there's an optimization piece to be done at REBA 3 and REBA 4. Insulation, again, another massive gain for the industry in terms of the improvement in performance we're going to see as a result of this change. In 2015 version, it referenced BS 5422, which is completely inadequate for getting kind of the losses that we need on heat networks. We've now moved to a prescriptive minimum 50 mil insulation thickness. Just a note on this, when you get down to the drop downs into the HRU, a lot of that will be fixed in terms of the space between your final pipe connections from the network, and you won't be able to get 50 mil on those terminal runs due to the space between them. That's fine. And in some areas, you'll need to actually drop down from the CP1 2020 50 mil requirement and drop down to maybe 35, 40 mil. But the key thing to do is to link your total heat loss calculation back to the minimum 100 watts per dwelling requirement within CP1 2020. So wherever you're having to make reductions on the CP1 50 mil reference, justify it by saying, I've either justified that my losses are 100 watts a dwelling, or increase the areas where you're less space constrained. So don't get too bogged down in CP1 says I've got to do 50 mil everywhere. Sometimes that's going to be impractical, but make sure you're tying it back to a reasonable loss calculation. Obviously, reducing operating temperatures, the smaller the difference we can get between our ambient temperature and our flow temperature and return temperature, the lower our losses be. But as I was saying, also that's a double whammy now, because our heat pumps also will operate more efficiently. This is actually a efficient performance profile for the Mitsubishi Chavs, which are very popular in the market for kind of 50 to 200 unit systems. They're very modular. And you can see that the COP curve against ambient temperature, if I just took a mean ambient temperature of 10 degrees, if I'm asking my heat pump to operate at 55 versus 65 degrees, I'm going to get a 36% increase in efficiency. And this all comes back to the decisions I said at the start of what do my dwellings receive and how many substations do I put in, because that's defining what operating temperature my heat pump will have to run at. If I add a heat exchanger, then I'm going to have to raise that by 5 degrees to get that transfer across. If I put in radiators sized for 70-degree flow temperature, there's no way I can ask the heat pump to operate at 65. So starting at the dwelling and linking it back is how we get the optimization of operating temperatures for heat pumps. You can see the size of the prize available there in terms of the efficiencies of getting those temperatures right. We really don't want the heat pump to be doing much more than 60 degrees. There are high temperature heat pump applications out there that can do more than 60 degrees. In general, the COP start in terms of running costs and carbon emissions. So that what you need to be thinking about in terms of designing heat networks and planning for heat networks is, I'd like my heat pump to be doing a maximum of 60 degrees, but ideally I'd actually like it to be doing more like 55 degrees. But as a starting point, 60 degrees is acceptable. Now on hot water, previously that would have been quite challenging, because on instantaneous hot water systems that the vast majority of heat networks are, we used to have to supply 55 degrees. We've done a lot of work in this space with CIBSE, actually. We're on the CIBSE Domestic Hot Water Working Group, and the outcomes of that research were that we have moved as an industry for instantaneous low volume systems where Legionella under HSG 274 is considered low risk. We only need to supply 50 degrees C to the outlet or upstream of a TMV that then obviously mixes that down. There's really only one gap in this now, which is NHBC, that has called for 55. Compensation for of NHB schemes under the NHBC 2019 through this justification, but we understand like this 50 degrees. So for the hot water generate, 50 degrees out from the HRU, which means we can bring 60 degrees quite comfortably to generate that 50 degrees hot water. Space heating is a bit more challenging now. If we want to get 60 degrees in and we want a temperature difference across our HRU of say 5 to 10 degrees for kind of reasonable, the HRU is not getting too big, but also stable control, we really want to put an upper bound of 50 to 55 degrees on our space heating system. Now, radiators traditionally have been, 10 years ago, maybe 80 degrees. Then we went through, 70-40 rads, and we're starting to get some 60-40 radiator systems designed. Dropping them down to 50, we're dropping those temperatures down. Yes, our fabric is improving and we should get gains from that, so our heat outputs can drop. But for a given heat output, our radiators are getting bigger because the surface area needs to increase. And they're starting to get quite large and sometimes untenably large in terms of the surface area we need if we're operating a 50-degree radiator. So underfloor heating, from our perspective, is a very attractive way of getting temperatures down because they operate more like 40 to 45 degrees, obviously much greater surface area. That a lot of developers are actually shifting to exclusive underfloor heating on their heat network systems. We can go direct and just feed the heat network 60 degrees into the 60-degree radiator. That only really works when you've got maybe less than 6-7 stories in a building, because the pressures start to become quite high and you don't really want those high pressures just passing straight through to the resident system. Just to put the radiator sizing impact in context, if we took a 70-40 radiator, the output from that, if I wanted to achieve the same output by operating at, say, 55-35, I've increased that by up to 160%. And then by the time I get to like a 50-30 radiator, I've doubled the size of that radiator. So I'm either making it twice as wide, or I'm making it, triple panel, or sometimes we see the floor to ceiling radiators. But we need to realize that early on in the design so that we're radiators in the flat. So understanding the impact of that early on is really key. Going back to the system sizing, CP1 2020 has now got a really clear direction on how do I diversify heating and how do I diversify hot water. Diversification is all about not assuming everyone is heating and hot water on full whack all of the time, because the data just shows that doesn't happen in practice. So there's a curve in the standard now for space heating, and by the time we get down to about 20-25 dwellings, then we diversify our heating demand by about 62%. And a lot of work went into arriving at a single diversity curve for hot water, which is actually the Danish DS439 flow rate equation. I'm not going to go into the details of this, but there's a legacy of around the Swedish standards was referenced. That gave a lower diversity than the previous Danish DS439 power curve approach. There was the Dresden standard reference. This is now the single authoritative CP1 referenced approach to diversifying hot water for the UK moving forward. So, the consultants I'd recommend going through the CP1 methodology, getting familiar with the equations and the approach, and there's a fully worked methodology for an example block of flats that also all the way through to how to size the pipes based on these diversities. So it's worth getting up to speed with that for new heat network project. One of the big issues of heat networks in terms of resident experience has been delivery of hot water, and it taking a very, very long time to get hot water on a heat network. And sometimes, residents won't water to even start feeling hot. The new CP1 2020 requirement is that for kitchen taps, which is obviously one of the most frequently used hot water outlets, and it needs to be hot for kind of dishwashing, is that it has to generate 45 degrees within 45 seconds. That's linked to the fact that 45 degrees feels really quite hot. You don't really need 50 degrees water. Most people would not feel comfortable putting their hand under 50 degrees hot water for very long at all. And what we're seeing is actually developers apply this to all outlets to try and get a really good resident satisfaction rather than just the kitchen sink. But from a CP perspective, it's just linked to the kitchen sink. The reason that we've had high losses, long delivery times on heat networks is that the pipework size to take the hot water that's generated by the HRU to the outlet has been too big. And the prime example, imagine the pipe size to a bathroom will be supplying a bath and a wash hand basin. Now the bath might need 12, 14 litres a minute, but the wash hand basin might need 4 litres a minute. If I'm sizing a 20 mil copper pipe to go from the HRU to that bathroom and then only drop down to, say, a 50 mil pipe at the bathroom to supply my wash hand basin, that 20 mil pipe, when I'm only pulling 4 litres a minute through it, it takes a long time to clear that volume of cold water that sits in that pipe in between hot water usage. And so what we actually need to do is move to an individually run and individually pipe sized based on the outlet flow rate approach using a manifold. So what we do is have the HRU, we come to a hot water manifold, and then we run individually to each outlet with a pipe sized for the flow rate that it needs. So the bath pipe sized for 12 a minute, but the wash hand basin sized for the 4 litres a minute. And they would have two different pipe sizes. The bath would have one and the wash hand basin, the smaller one. We did a lot of work on this. We did some in situ trials for one of our developers who wanted to really get to the bottom of this issue. Incidentally, our writing into this year's CIBSE technical the research of this trial and our recommendations to the industry of what to do with the research that we've done in terms of delivery times. The theoretical calculation of how long does it take to clear that volume of cold water, plus how long does it take the HRU to give me hot water, actually held true to what we tested in practice. So you can see that on this curve here, where we've got, we've turned a kitchen sink tap on, and it's a 5 metre run of pipe work with a 14.2 mil ID, 6 litres a minute. It took just under 10 seconds to clear that volume of pipe work. The HRU took circa 5 seconds to get hot, and then we started seeing 45 degrees C at the outlet, and that only took 14 seconds to do so. When we do the same test, but the run is 25 meters long, what happens is you get your theoretical calculation of time to clear that cold water, which for this is about 40. We've got that same HRU warm-up time, another 5 to 10 seconds. So we should be seeing hot water come out within 55 seconds, if that theory was true. But what actually happens is we start to see warm water and hot. And what's happening is that pipework that was cold is cooling down the water as it balances to a temperature before it gets to the outlet, and that effect is really exaggerated for long runs of pipe work, and that was being missed by the theoretical calculations. So we had systems where the theory said, no, it should get 45 and 45, but actually it was taking 90, 95 seconds. Paper that gives some empirically based calculations to be able to work out what is that elongation of cool down effect from the pipe work. And if you want to be hitting your 45, 45 when we're testing them, it's going to be really critical design decisions to make. So it's one to look out for when the symposium paper comes out, but also be thinking about adding in some margins for cool down effect for anything 10 to 15 meters or above in terms of length. And this is schematically what this kind of system looks like. So we've got our heat interface unit here. We come with a common copper pipe to a hot water manifold. We want to keep that common pipe less than half a meter because we don't want that large pipe run to be very long. And then what we're doing is running individually. So we're running to the bath, we're running a 16 mil medium layer composite pipe here, but to the wash hand basin, we're running that in 12 mil. That's a small bore pipe, so it's that's what's needed to get decent delivery times to a low flow rate application. And then we're running to our shower in a 16 mil that's got a high flow rate application, but our kitchen sink again is only receiving a 12 mil pipe. So that's the kind of approach we're going to need to start seeing to hit 45 degrees in 45 seconds across the board. Last kind of technical one, demonstrating the importance of performance monitoring. This is a graph of being able to use the data to identify a fault and then be able to rectify that fault and show the impact of it. So what we've got here is a network where we can see that the on the bottom, the return temperature is extremely high. So we've got a flow temperature of 67, 70 degrees, but our return temperature is really high, so it's above 60 degrees. And what's happening, the bypass is open. We use the data to diagnose where that bypass was, shut it, and then you can see the immediate impact of just one bypass being shut on the network return temperature. So just by having that access to that data alone, we've dramatically improved the performance of the entire network due to one small issue that without that diagnostic information would have been incredibly time consuming to find, diagnose and rectify. And this immediately drops the heating bills to all residents in the building. So can't stress enough the importance of being able to monitor the data of your heat network if you want to keep it performing well. And it's also just as important during commissioning to be able to find these faults before it gets handed over. I could talk again for an hour about how to deliver heat networks, quality assurance. That's what I spend the vast majority of my time and my team's time doing. But it's really a people thing and a process. But going from a design to installing that design and commissioning that design, it changes hands a lot. There's lots of stakeholders involved. Lots of conflicting priorities, program, cost, and what you need to do is build that performance in, make sure that performance is protected, improved, make your processes, your quality assurance processes transparent up front with the stakeholders. So sit down with the commissioning entities, sit down with the installation contractors and say, I'm a quality assurance provider for this heat network. This is how we're going to do it. This is the performance metrics we want to achieve, and build trust and collaboration with those partners. Don't come in at the 11th hour, start testing their system. It's a surprise to them and start criticizing their work. That just doesn't produce good results. You've got to verify the performance. That's absolutely critical. And you do need a level of independent testing to do that. But you've got to build the trust and collaboration. They're very complicated delivery systems, lots of moving parts, lots of different stakeholders, and the main thing is to be transparent and to build that trust from day one. And the most enjoyable projects for me and the ones where we get that high performance at the end is where I've struck that collaboration. Actually, that Norfolk is up for the CIBSE Building Performance Award for the collaboration activity. So that's kind of really what I'm driving here is that if you want to deliver successful heat networks, you're going to get into the people side of it and collaborate with people, and that requires a lot of trust. And that's my last slide. Is Stephen still there? I think someone was going to curate, but I can try. By the way, my headset keeps telling me I need to charge it. So if it suddenly drops out, that's what's happened, and I will try and plug a lead into it. But if you lose audio, that's what's happened.
That's great. No, that's fine. Thanks, Mike. That was very informative, very interesting. Excellent. There are a number of questions here, so I'll start off with Chris. Has there been an analysis of the operating costs of the heat pump revolution as opposed to the carbon savings and the social impacts of increased energy bills? So
there's a lot. There's a lot in there, Chris. Yes, there's a lot of analysis going on the cost of heat pumps. I mean, fundamentally, to electrify heat compared to gas, and I'm probably going to talk about this from gas and electricity prices 6 months ago rather than what's going on now in the volatility. Electrifying heat is going to cost more than individual gas boilers. There's ways we can reduce that. I do think there'll have to be support from the government in terms of how do we stop particularly fuel poverty residents paying for decarbonisation of heat, but you can still get with appropriate design, good selection, heat tariffs of 5 to 6 pence a kilowatt hour so it's achievable, but a lot of work needs to go in to avoid making decisions that make the running costs quite high. Carbon saving, as opposed to carbon savings, social impacts of increasing energy bills. I think it is going to be a challenge, and I do think policy will need to support it. I think the London plan and the way the GLA is positioning its carbon tax is actually very effective at the moment in terms of incentivizing a high degree of decarbonisation. But I think there's probably going to have a lot more to be done in terms of the impact on running costs of residents of electrifying heat.
Yeah, thanks, Mike. This is more a product question. What are the most important features of a heat interface unit?
Yeah, so return temperature performance. It shows you those graphs, like getting those low return temperatures, which is dictating what half the system losses will be. The HRU is one of the most important aspects of getting those low return temperatures. So whether it's in hot water mode, space heating mode, or standby, the HRU is largely going to determine, for a given well-commissioned dwelling, how much you're able to transfer low return temperature back to the network. So pretty much the most important feature to look for when you're selecting HRU, and I would always recommend only selecting beta tested units because that performance is benchmarked. You know what you're getting, yeah, that's a minimum requirement for me. And I would always also recommend specifying a minimum return temperature performance across the 3 modes that's been tested under the BESA.
Right, great. I don't know if you got any idea of
this.
What's the capital cost pound per kilowatt benchmark for electric boilers?
Quite similar to the gas boiler one I mentioned, but some got the flue. They can sometimes be a bit lower. So I don't quote me on it, but yeah, around 65 to 80 pound a kilowatt for a commercial electric boiler is what we're seeing.
Yeah,
and the electric boiler one is a really interesting one because people will think of hybrid systems as air source heat pumps and gas when you don't necessarily have to do that. You can do a 95/5 system where the heat pump's doing 95% generation and the boilers are doing 5%, and that can come from an electric boiler. You don't want an electric boiler doing too much because obviously electricity is expensive. So if you start doing 20% of the annual heat from an electric boiler, the heat tariff is going to go up. But if you limit that, then they can give you a vehicle of getting off gas completely on day one without putting in 100% air source heat pump or ground source.
Great. Another one from Chris, similar to before. This is about risk of social exclusion in terms of those who cannot afford complex multi-source systems compared to particularly on retrofit projects. How can we fund the transition and do it at scale?
Well, I mean, hybrid systems are, if we want to do heat pumps, I'm passionate about doing hybrid systems for this very reason, because I think they can reduce the capital cost that the resident will ultimately have to bear, but give you a big impact of decarbonisation. So the hybrid one is a way of keeping those costs down rather than fully moving to heat pumps. But in terms of the social impacts of these things, there's the reality of decarbonising heat, of electrifying heat, and obviously we've got extremely volatile utility prices. There will have to be, in the long, I think there will have to be interventions to avoid fuel poverty.
Yeah. Question from Charlie: is there scope to use water source heat pumps in the tertiary system if the required domestic hot water temperature is higher than the heat network flow temperature, e.g. in a GP surgery?
Yes, there is. So that's effectively an ambient loop system where you have a central heat pump generating, rather than up to 6 degrees, more like 30 degrees, and then the water source heat pump in the dwelling to serve a cylinder that takes you 30 degrees 60 degrees for hot water storage. Typically, those systems will be more capex intensive than a low temperature heat network. Those systems are really come into their own when you have both heating and cooling, because that water source heat pump is probably going to cost you about £4,500 a dwelling, whereas an HRU will cost you about £1,500 a dwelling. Obviously, if there's a cooling demand in every property, then if you're going to do that with a heating and chilled network, you're doubling up on things, and so the costs can start comparable. If you're looking at that sort of thing, you need to get right into the detail and understand the pros and cons of each system. But in terms of the required domestic hot water temperature, if you're moving to instantaneous, there's no reason why it shouldn't be doable. It's only if you're looking to retain storage that it might become an issue from a Legionella. But I would always push you to try and avoid storage and go instantaneous for this very reason, and then get the temperatures down.
Great. Question from William. What happens if on the coldest day the water source heat pump freezes the water?
Well, I mean, that would, obviously wouldn't be good. We need to avoid that through appropriate design, selection and commissioning. And that is a really good point, that, the heat pump selection, devil is in the detail, and you need to look at the operating curve, and some of them just switch off. So they can look really good. They're generating 60 degrees, good COPs, but below -5 degrees, they stop. So if that's your only generating asset, and we get a beast from the east, then that's an issue. And to be honest, like things like beast from the east are going to be challenging for air source heat pumps, because if you look at, what do we design to for our external ambient condition? -5 degrees, depending on where we are, -3. Like, it's not a design requirement to design for -20, but we see it. So it's a good question. A lot of thought needs to be put into it in terms of the design, and it will come down to the right heat pump selection and then the mitigation measures putting in place for extreme conditions. But again, hybrid systems having an additional heat generation source backup to avoid heat pumps being the one and only generator, I think, is a good way of de-risking that.
Yeah. Question from Vince. Have you any data insight into the whole life carbon of a heat network, i.e. the embodied carbon associated with the distribution pipework equipment, large-scale distribution plant versus localized small-scale heat generation? And some Adam Adain has referenced TM 65.1.
Yeah, so sorry, I don't have any data personally or company in terms of the whole life carbon. We've got a lot of data on the operation and efficiency of heat networks in terms of the efficiency of the generation assets and their carbon intensity, the heat losses, so the carbon intensity of heat served. But I think for data, kind of whole life and embodied carbon on the materials, I would look to benchmarks that someone like Aidan has put up. So I don't have operational and specific data on that. Apologies.
Question from Stuart. Do you know of any low-cost software or tools which assist with the sizing of heat network pipework as a complete system rather than individual pipes, like freely available software similar to HypeSoft?
I don't, off the top of my head, no.
No. Neither do I. William, another question from William. The issue of pipe size and losses are complex, as with high flow temperatures such as 90 to 95, flow and return temperatures, say 40 degrees C, the pipes are so much smaller than one designed for, say, 60 degrees C, that the heat loss and costs are actually much lower. It is counterintuitive, but it's worth running the numbers.
Okay. The challenge with that is, where do you get the 90 to 95 degrees from at scale across the country in terms of heat pumps? Yeah,
exactly. A question from Terry. Where would you locate a TMV on a manifold system?
So they're normally local to the outlet of which they're mixing down.
Great. Question from Lucy. Do we know if there's any effort to translate the new installation requirements in CP1 Mark II into a British standard?
Yes, there is. There's actually a British standard BSI working group on BS 5422 upgrade group. I don't know the timescales of when that's coming out, but it's basically in CP1 2020. So yeah, I know that's a work in progress.
Right. Yeah, comment from Phil Jones, fantastic, and I agree, fantastic presentation. I agree 100% with everything Mike has said. Can I also say thanks and appreciation for the huge contribution Mike and colleagues Tom Norton and Gareth Jones made to CP1 2020. The UK heat network sector is making massive strides forward in relatively short timeframes, onwards and upwards to heat network zoning and regulation. Well done, Mike, tremendous stuff. Great.
Thanks, Phil.
Yeah, that's that. William has also said excellent presentation.
Thanks, William.
And Nathan has a question: what happens with a hot water cylinder with regards to temperatures from heat pumps?
Yeah, so hot water cylinders are a challenge because they need to have the 60-degree purge from a Legionella perspective. So, you know, if you start then adding heat exchangers, you're pushing that temperature up to 65 or 70. So it's very project specific. I mean, try and get rid of them. We're doing retrofit projects where cylinders and we're actually taking the cylinders out and moving to an instantaneous system. But where they are, you know, the lesser of two evils, sometimes does it need some electric top up for just purging in periodic times. But fundamentally, the cylinders will need a higher flow temperature from the network than an instantaneous.
Yeah, yeah.
You can go direct into the cylinder, but I've had, I know of horror stories where, if you think about it, your network is then feeding into the coil of the cylinder. If that leaks, you're actually passing, you know, treated water into the, you know, that person's available hot water system. So I'm quite of direct hot water into cylinders.
Comment: who needs a BSI when you have CP1? Thank you from Chris Jones. Another question: around 50,000 HIUs have been sold each year, which shows the size of the heat network sector. CP1 requirement is there to be tested under BESA test regime to ensure performance, but installed commissioning is key. Can you outline just how important certification and quality assurance is going to be in the future?
Yeah, I mean, it's going to be absolutely critical. So heat networks are going to be regulated. The timescales of that regulation is a bit unclear, but we know that it's going to be the next regulated utility. It's going to be, you know, an off-gem type regulation, and BEIS have made it pretty clear that technical standards are going to be at the heart of that regulation, and there will also need to be a level of independent certification against those technical standards. And I think it's quite likely that CP1 will form the backbone of the start of what those technical standards are. So certification and quality assurance is critical from a developer de-risking their regulatory exposure. It's also critical for heat network operators potentially becoming licensed operators once BEIS confirm what that will be. But also from an ethical level and protecting heat networks, which couldn't be more vehicle for us decarbonising in the UK. High quality heat networks where we have really high resident satisfaction is what we need for the industry to continue to grow. If we keep, if we deliver poor heat networks and residents complain and that gets in the news and then government get pressure, we're going to lose this opportunity and we won't be able to hit the decarbonisation targets that we need to. And so regulatory de-risk, but also just fundamentally to get heat networks working well, assurance and quality is key.
Yeah, thanks from Vince, thanks from Lucy, excellent presentation, Francesca, much appreciation, Chris Jones. Copper/silver water treatment can allow low temperatures, no pasteurization of domestic hot water and lower systems losses. Have published a white paper with published a white paper with very impressive stats. Comment. Thanks, Michael. Great stuff from Chloe. This has been a great and really informative. Thanks very much from Paul. Question.
I'll send them through. This video will also, I think, be on the CIBSE YouTube.
Yeah, exactly. Do you have a view on the incorporation of heat batteries into primary, secondary, tertiary systems? Great presentation. Question from Mark.
Batteries, I'm not sure, heat batteries, if I've understood that correctly, Mark. We have done an assessment of using a large commercial battery within an energy centre to give you flexibility in when you run your heat pump, and also to shave your peak load. One of the big issues with electrifying heat is we're putting that load. A lot of load is going on the grid as we kind of get access to this low carbon electricity that renewables have given us. But that it has a breaking point, and it has a breaking point in terms of capacity, but also in terms of distribution. And so developments that used to have an electrical load, when they want to put a big heat pump in, they're now asking for a lot more. And so we looked at could we have an on-site battery that allowed us to, in a similar way to a thermal couple, when we wanted to run the system, to shave that peak load. Of cost of batteries, the fact that you have to replace them every 10 to 15 years, the commercials just didn't look on the face of it to stack up. But I do think more research should be done in that area, because I think one of the biggest risks over the next 10-year period, as we really do get more heat pumps onto the grid, is at what point does it start creaking and becomes a bottleneck. So I think research into battery storage to help that would be good.
Great. Yeah, lots of thank yous from Stefania, Frank, Simberg, Seekle and Andrew, and I think that's all the questions, Mike. So I just to thank you for excellent presentation, and the number of questions just shows how much interest there is in this subject. So thanks very much. And again, the presentation will be available on the CIBSE website, and a copy of this recording of this presentation will be on CIBSE YouTube. So yeah, please check in again, and yeah, I'd like to wish everyone a good evening, and especially you, Mike. Thanks again, much appreciated.
You're welcome. Great to see so much interest in heat networks.
Isn't it? That's great. Thank you again. Have a good evening.